Risk analysis of Eichhornia crassipes invasion and hydrocarbon synthesis for lead removal from water. Introduction. Water is fundamental for the sustenance of all forms of life on the planet and satisfies the basic needs of the population. However, water resources are limited and are threatened by pollution, mainly generated by human activities. Alterations in water quality make ecosystems susceptible to invasion by alien species. Invasive species, unlike native species, are those that are present in a region due to human actions, whether intentional or unintentional, and which have allowed them to overcome biogeographical barriers. These species have significant impacts on ecosystems, the economy, human well-being, and alter the water cycle and chemistry. Water hyacinth, Eichhornia crassipes, is a common invasive species in water bodies, native to the Amazon basin and has been cataloged as one of the most difficult aquatic weeds to control. It is also considered one of the 10 most problematic invasive plants in the world due to its rapid spread and high biological productivity. This species has a remarkable ability to reproduce both asexually through stolons and sexually through seeds. It is tolerant to a wide range of temperatures and nutrients, and under optimal conditions its proliferation is even faster. On the other hand, in San Luis Potosí, Mexico, the presence of water hyacinth has been reported in the San Jose Dam, which supplies 8% of the population of the state capital. Previously, actions have been taken to control the presence of water hyacinth in the Jose Dam. However, these efforts entail high costs and secondary environmental impacts and do not always provide satisfactory results. Based on the above, it is necessary to implement management and harvesting strategies that allow for the sustainable use of water hyacinth biomass. This biomass is widely available in large quantities and at low cost, and its conversion into a carbonaceous material represents an opportunity to mitigate its negative impacts. In this sense, it is relevant to highlight that water hyacinth in dry weight is composed of 33% hemicellulose, 25% cellulose, and 10% lignin, which makes it an attractive biomass with multiple applications. The aims of this work were: evaluate the risk of invasion by water hyacinth on the surface of the San Jose Dam, San Luis Potosí, Mexico, to valorize water hyacinth biomass through the synthesis of hydrocarbons and evaluate their effectiveness in the removal of lead present in aqueous solutions, characterize the hydrocarbons to determine their physicochemical properties, and elucidate the possible mechanisms of lead adsorption. Methodology. The water hyacinth invasion risk analysis at the San Jose Dam was carried out using the Aquatic Species Invasiveness Screening Kit version 2.4. This tool is composed of 55 questions, 49 of which correspond to the Basic Risk Assessment, BRA, and 6 to the Climate Change Assessment, CCA. The water hyacinth plants were washed with water. Subsequently, plant parts were separated into leaves, LE, stems, ST, and roots, RO, to prepare different hydrocarbons. The synthesis of the hydrocarbons was carried out using a D-optimal response surface experimental design to evaluate and optimize the effect of the synthesis conditions on the properties of the hydrocarbons obtained. The hydrothermal carbonization was carried out in a stainless steel reactor, where hyacinth biomass was placed in deionized water with a 1:10 ratio. Then, the reactor was placed in a muffle at 220 degrees Celsius with different residence time: 2, 3, 4, 5, 6 hours. Finally, the synthesized hydrocarbons were washed with acetone, ethanol, and deionized water and dried at 100 degrees Celsius for 24 hours. The adsorption of lead on the hydrocarbons was evaluated by batch experiments at different pH values, 3, 4, and 5, and 25 degrees Celsius. Subsequently, the pH value where the highest adsorption capacity was obtained was selected to evaluate the effect of temperature at 10, 25, and 40 degrees Celsius. Lead concentration was determined using atomic absorption spectrophotometry. The maximum adsorption capacity was evaluated with Langmuir and Freundlich isotherm models. The physicochemical characterization of the hydrocarbons was performed with the following analytical techniques: scanning electron microscopy, nitrogen physisorption, infrared spectroscopy, thermogravimetric analysis, surface charge distribution, and zero charge point. Results. Invasion risk analysis. The risk assessment was conducted by assigning a response to each question. A confidence level and justification was provided, and the scoring results, ARB and ARB plus CCA, were obtained. Low risk is considered when the score is less than 1, indicating a low probability of the species becoming invasive in the assessed area. On the other hand, a score less than or equal to 1 represents a medium or high risk. The risk of water hyacinth invasion determined for the San Jose Dam was high. Experimental design. The optimal response surface, Table 2. Dependent variables, carbon percentage, and lead adsorption capacity. Independent variables, residence time and plant component, LE, ST, and RO. Maximum yield percentage values were reached after a residence time of 2 hours, registering 55.05%. As for the carbon percentage, the highest value obtained in the hydrocarbons synthesized for 6 hours, with 66.2%. The maximum lead adsorption capacity was 69.49 milligrams per gram, achieved with a time of 6 hours. The hydrocarbons obtained in treatments 3, 5, and 9 showed the best results in the variables evaluated. These materials were selected for characterization and to evaluate the effect of pH and temperature on lead adsorption capacity. Figure 2a shows the response surface for the yield percentage, where a descending slope is observed along the time axis, indicating that the values decrease as time increases from 2 to 6 hours. However, along the axis representing the type of plant component, a constant behavior is observed, with no significant variations. In contrast, Figure 2b shows the response surface of the carbon percentage model, in which an inverse effect is seen on the time axis, with an increase in carbon percentage as time increases from 2 to 6 hours. As for the plant component type axis, no significant changes are observed, remaining constant. Finally, Figure 2c presents the response surface of the lead adsorption capacity model. Here, an inverse parabola effect is observed along the time axis, with maximum values at the 2 and 6 hour limits and a minimum value at 4 hours. Likewise, along the plant component type axis, a parabolic effect is observed, where the material coming from the stem, 0, presents the maximum value, while the minimum values correspond to the extremes of leaf, -1, and root, 1. Scanning electron microscopy. Figure 3, A, B, A, C, and E shows an irregular, compressed, and fragmented surface with small pores. This can be attributed to the carbonization temperature, 220 degrees Celsius, which causes the degradation and hydrolysis of cellulose and hemicellulose. In Figure 3, B, D, and microparticles can be seen agglomerated on the surface of the hydrocarbons. Nitrogen physisorption. The values in Table 3 correspond to mesoporous-type materials according to the IUPAC classification. The nitrogen adsorption isotherms on HLE, HSD, and HRO exhibit type 2 behavior and H3 hysteresis of mesoporous materials, Figure 5. Surface charge distribution and zero charge point. According to Figure 5, HLE, HSD, and HRO exhibit a positive surface charge in the pH range from 2 to 6, pH lower than zero charge point, and presented a negative surface charge in the pH range from 6 to 10, pH higher than zero charge point. According to the above, HLE, HSD, and HRO exhibited a positive surface charge in the pH range from 2 to 6, while they exhibited a negative surface charge in the pH range from 6 to 10. The variation in charge distribution related to the zero charge point of HLE and HSD at pH values greater or equal to 6 could cause electrostatic attraction between lead and the negatively charged surface. In contrast, HRO has a zero charge point of 5.2 and a higher concentration of total acid sites, which influences its adsorption capacity due to competition between lead ions and hydronium ions for the surface active sites. Infrared spectroscopy. The IR spectra of HLE, HSD, and HRO after the adsorption process, Figure 6, show slight changes, indicating interaction between the materials and the lead solution. The peaks at 780 methyl, 1300 carbonyl, and 1603 cm1 alkene were attenuated. This may be attributed to the ability of heterocyclic compounds, alkene, to donate electrons, interacting electrostatically during lead adsorption. The shift of the aromatic alkene bands at 1603 and the methyl bands at 780 cm One suggests an interaction between lead and pi electrons. Thermogravimetric analysis. The combustion process of hydrocars is divided into 3 stages. Figure 7. 1. Weight loss due to water evaporation at temperatures below 150 degrees Celsius. 2. Weight in the range of 300 to 400 degrees Celsius, caused by the decomposition of hemicellulose and cellulose. And 3. Weight loss between 420 and 800 degrees Celsius, attributed to the decomposition of lignin. Effect of pH and temperature on lead adsorption capacity. Increasing the pH improved the adsorption. The experimental data were fitted to the Langmuir isotherm model. The maximum adsorption capacity, milligrams per gram, was achieved at a pH of 5, with values of 130.3 HLE, 125.3 HSD, and 86.7 HRO, figure 8a, B and C. Similarly, increasing the temperature enhanced the adsorption capacity, milligrams per gram, with values of 164.6 HLE, 171.0 HSD, and 131.4 HRO at 45 degrees Celsius, figure 8c, D and E. The proposed for the removal of lead on hydrocars include microprecipitation, confirmed by scanning electron microscopy, figure 3b, D, and F, electrostatic attractions as indicated by zero charge point values, figure 5, and chemisorption corroborated by infrared spectroscopy analysis, figure 6. Conclusions. Risk of water hyacinth invasion on the surface of the San Jose Dam, as determined in this study, was high according to the ASSIST results. A response surface experimental design was used to perform hydrothermal carbonization of water hyacinth biomass, providing a viable option for its utilization and offering a sustainable environment management alternative. Characterization using various analytical techniques confirmed the efficiency of lead removal from aqueous solutions. Acknowledgements. Thanks. The CONACYT and COPACYT.